Hey everybody, my name is Kelvin and welcome back to my channel. In this video, we're going to be talking about neural networks and how to build your first one in Python. Neural networks can feel confusing and hard to picture, especially for beginners, and this video is meant to help make it click for you guys. We'll start by talking about what a neural network actually is, what it's going to do at a high level, why people use them, and then we'll build one together in code. Real quick before we jump in, if you've been enjoying the content on this channel and want to support what I'm building here, check out my book Modern Data, From Ingestion to Production. It's a practical introduction to how data actually moves through modern systems, from ingestion and transformation all the way to production use. It's available on Amazon, Barnes & Nobles, and Apple Books, and the ebook is only $6, so it's a pretty affordable way to support the channel and learn something useful at the same time. I'll have the links in the description. If you'd like to follow along, I have all the code and the notebook in a GitHub repository linked in the description. Let's dive into neural networks. So let's start with the main question. What actually is a neural network? At a simple level, a neural network is simply a model that learns patterns from data. You give it input data, it passes the data through a series of layers, and it produces an output. During the training phase, it adjusts internal values called weights, so that its predictions get better over time. That's it at the highest level. A lot of the terminology around neural networks can make them sound a lot more mysterious than they actually are, but at its core, a neural network is just a system for learning a relationship between inputs and outputs. For example, if I show a network a lot of examples of handwritten digits and tell it which digit each image represents, the network can gradually learn what kind of pixel patterns tend to correspond to a 0, or a 3, or an 8. At the beginning, your neural network doesn't know anything useful. Its predictions are basically random, but after seeing lots of examples that you give it, measuring how wrong it was, and updating the internal parameters, it then improves. That process of improving from data is what makes it a learning model. For this video, we are going to build a neural network that classifies handwritten digits. The input will be an image of a handwritten number, and the output will be the network's prediction of which number it thinks the image represents. This is called a classification problem. Why? Because we are taking an input and assigning it to one of several classes, or several categories. In this case, for handwritten digits, the categories are the digits 0 through 9, so in this case, there are 10 total classes. That means by the end, our model needs to look at an image and decide which of those 10 categories is the best fit. To do this, we're going to be using a very popular beginner dataset called MNIST. MNIST is a dataset of grayscale images of handwritten digits. Each image is 28 pixels by 28 pixels, and each one has a label telling us what the digit actually is, what the true value is. That makes it a perfect starting point for learning neural networks because the images themselves are small, the task is very easy to understand, and the dataset is already built into Keras, which means we can spend our time learning the model instead of having to hunt around for data files. Now you might be wondering, how does a neural network, quote, see an image? To us, right, these are just regular images, but to the neural network, these are numbers. Each image is a grid of pixel values. Because MNIST is grayscale, meaning every pixel is just a single intensity value, brighter and darker parts correspond to different numeric values. So the model is not seeing a handwritten 7 the way we do. Rather, it's seeing a pattern of numbers that is arranged in a 28 by 28 pixel grid. And in a simple neural network like the one we're building today, we're going to flatten each image into a 1D list of numbers. Since 28 times 28 is 784, and each image will become a vector of 784 input values. A basic neural network is usually made up of 3 different kinds of layers. 1, an input layer, 2, one or more hidden layers, and then finally an output layer. The input layer is exactly what it sounds like. It's where the data comes in. Then the hidden layers are where the model will learn patterns and transformations, and then finally the output layer gives us the final prediction. In our case, the input layer will accept 784 values that we've established, The hidden layers will then learn from those values, and the output layer will have 10 neurons, one for each possible digit. Let's start in Python by importing what we need. First, we'll need NumPy, and we can import this by import NumPy as NP. It's one of the most important Python libraries for numerical data. Matplotlib right here is what we'll use to show images and then plot our results. TensorFlow is where the magic happens. TensorFlow is the deep learning framework that we are using underneath everything. Next, Keras. Keras is the higher level API that lets us build neural networks in a clean and readable way. And then this import statement right here will give us direct access to layer types like dense, which we'll use to build the model. If you need these packages installed on your virtual environment or machine, just uncomment this code right here, and I'll have all the packages that are required in requirements.txt. Let's run this and import everything. Now, let's jump down here and import the data. And we can do so using this line of code right here. This line is doing a whole lot. So let's break it down. First, keras.datasets.mnist.loadData. What is this doing? This returns the dataset that's already split into two parts. First, a training set, then a test set. And in each one of those parts contains the inputs and the labels. So what do I mean here? Xtrain here is the training images. Ytrain is the training labels. Xtest right here is the test images, and Ytest are the test labels. The X values are what the actual data that the model will learn from. The Y values are then the correct answers. That's all this line is doing right here. Let's run this, and we'll load our set. Whenever I load a data set, one of the first things that you should do is inspect the shapes. We can run this. We can see that Xtrain shape gives us something like this, 60,000, 28, 28. What does that mean? That means there are 60,000 training images that it's going to be learning from, and each image is a 28 by 28 pixel image. And if you jump down here, this is for our test data set. We have 10,000 test images, and those also are 28 by 28 pixels. And we can confirm that we've loaded our dataset correctly, the MNIST dataset from above. Jumping down here, let's visualize some examples. I want to look at a couple of the images. Our plot.figure right here will create a figure and set the overall size of this. And then we'll do for I in range 8, which we loop through the first 8 training images. Then right here, we're going to be telling the matplotlib to arrange the plots in a grid with 2 rows and 4 columns. And then here, we'll just show, we can run this, and we'll see that we have our images 5, 0, 4, 1, 9, 2, 1, 3, and their actual labels, that being a 5, a 0, a 4, a 1, and so on. Before we do anything, we have to pre-process the images. The first thing that we want to do is normalize the pixel values. The original pixel values are typically stored as integers from 0 to 255, but after division, we want decimal values so we can convert them into a floating point type. Since pixel values go from 0 to 255, dividing by 255 scales everything into a range 0 to 1, and this will be how we normalize our pixel values. This is a common pre-processing step in neural networks because models will tend to train more smoothly when the inputs are scaled to a smaller range, and we can do this for both training and test data because they need to be treated consistently. And we'll run this. We can see that it runs correctly. Now, we'll need to reshape the images into the format our dense neural network expects. This is one of the most important pre-processing steps in this video. Right now, as we said, each image is a 28 by 28 grid, but a standard dense neural network expects each example to be a 1D vector. So we flatten each image. Since 28 times 28 is 784, every image becomes a vector of length 784. And this is what these two lines are doing. What does this -1 mean here? In NumPy reshaping, -1 basically just helps us figure out the dimension automatically. We're basically saying here, keep however many rows are needed, but make each example length 784. Now, we'll run this, and then now we can see that the new shape becomes something like 60,784, because this is now a 1D vector, and the same thing with xtest. So now every image is represented as simply one row of 784 input features. At this point, we can already reason about the general shape of the model. Each input example has 784 values, and so our input layer must accept 784 features. Since we're predicting digits 0 through 9, our output layer must produce 10 outputs. That means before we even write the model, we already know that the input size is 784, and then the output size is 10. Everything in between is the hidden part of the network where the learning happens. Let's build our neural network. This is our model definition right here. We're going to be using Keras.sequential, which means we are stacking layers one after another in a straight sequence, hence sequential. That makes it a really good choice for a beginner model because the data just flows from input to hidden layers to output. Let's go line by line here, since this might seem like gibberish to you right now. We have this comma in here because we know that each one of these is in one-dimensional input shape. Our first hidden layer is this dense layer right here. This creates a dense layer with 128 neurons. Dense means each neuron in this layer is connected to every output from the previous layer. So each one of these 128 neurons will receive information from all 784 input values. The activation function here is ReLU. ReLU stands for Rectified Linear Unit, and its job is simply to introduce nonlinearity. This matters because if we did not use nonlinear activation functions, the network would be much more limited in what it could learn. Our second layer here is another dense layer, now with only 64 neurons. The layer takes the output from the previous hidden dense layer and it transforms it even further. You can think of hidden layers as the learning intermediate representations of the data. They are not just memorizing digits. They're actually just learning useful combinations of input values that can help with the final classification. And now, finally, we have our output layer. And you can see that we define 10 neurons here because we have 10 classes. The softmax activation converts the raw output values into probabilities that all equal to 1. So for one image, so the model could give us something like this. It could give us 0 has a probability of 0.01, 1 has a probability of 0.02, 2 is probability of 0.9, and 3 is possibility of 0.01, and so on. In this case, our most likely candidate here would be a 2, and it predicts with 90% confidence that the number that we've inputted is actually a 2. The class with the highest probability here will become the final prediction. Why do we need hidden layers? The reason is that hidden layers will allow the model to learn intermediate transformations of the data. If it went directly from input to output with no hidden layers, the model would be much more limited. By having hidden layers, the network can gradually transform the raw input values into more useful internal representations of the final task. It's one of the main reasons why neural networks are so powerful, since they don't just make a prediction directly from raw inputs, and rather they learn layers of representation in between. I've already printed a model summary right here, and this is one of the most useful things that you can do after defining a model. Our summary here will show the layers in order. We can see our dense layers right here, the output shape at each stage, see right here, and the number of trainable parameters. The trainable parameters that we see here, or total parameters here, are the weights and biases that the model learns during training. So when we say the model is learning, what it really is doing is just updating those parameter values. For example, the first dense layer has a lot of parameters because every one of the 784 inputs connects to each of the 128 neurons, and each neuron also has its own bias. That adds up pretty quickly. This is useful here because the summary will help us turn the abstract idea of a neural network into something a bit more concrete. Now, let's compile the model, and we can do that using this call right here. What do these mean? Optimizer here will control how the model updates its weights. Atom here is a very common default choice because it tends to work well and it's very beginner friendly. You can think of the optimizer as a method that takes the model's mistakes and then turns them into weight updates. Our loss function right here, we're going to be using sparse categorical cross entropy. The loss function here tells the model how wrong it is in its predictions. Since this is a multi-class classification problem and our labels are integers like 0, 1, 2, and so on, sparse categorical cross entropy is a great choice. The word sparse here matters because it means the labels are stored as integers rather than one-hot encoded vectors. Then finally, we have metrics. This tells Keras to track accuracy during training and evaluation. Loss is what the model is trying to minimize, but accuracy is often easier for us humans to interpret. So our compile here is where we define how the model learns, how error is measured, and what metric that we care about. We'll run this. Again, at the start, the model's weights are random. That means its predictions are not good at all. During training, the model will make predictions, and then those predictions are compared to the correct answers. The loss function measures how wrong the model was, and then the optimizer updates the weights to reduce that error. This process happens again and again and again and again across many batches and many epochs, or passes through the dataset. The core of neural network learning is the process of gradually improving the internal parameters so that the mapping from inputs to outputs gets better. Let's actually train it now. This is probably one of the most important lines in our entire script right here. Our model.fit here will start training. Basically tells the model here, here's the data, here are the correct labels, and then now learn from it. Xtrain here are our training inputs, and these are our normalized flattened images that we prepared above. Ytrain here are the correct labels for the training images. With 10 epochs, here we mean 10 full passes through the training data. Batch size of 32 is that the model does not update after seeing the whole dataset at once. Instead, it will process small chunks of data called batches. Here, each batch contains 32 images, and we've set it as such. So, it makes predictions on 32 examples, computes the error, updates the weights, and then it moves on to the next batch. Our validation split here is 0.1. This sets aside 10% of the training data for validation. The model does not use the portion to update weights. It only uses it to measure performance after each epoch. This is helpful because it gives us a sense of how well the model is doing on held out data during training. And then we'll just simply store all of this in a variable called history. History contains the training metrics from each epoch, like accuracy and loss. We'll use this to make plots later. Now we run this, and it'll train right here. Usually this takes a little bit of time, so there will be a cut in the video after it's done training. We've only set it to 10 epochs, so it shouldn't take longer, but more complicated and sophisticated neural networks can go on for hundreds of epochs. And we're done training here. During training, you might have noticed that Keras gives us a few important values per epoch. We'll see loss, accuracy, val loss, and val accuracy. The loss here tells us how wrong the model is on the training data. The lower the loss, the better. Loss is not the same thing as basically getting % wrong. It's rather more a detailed mathematical measure of how far off the model's predictions were. So if loss is going down over time, that usually means the model is learning. Next, we have accuracy. Accuracy tells us the percentage of training examples that the model has classified correctly. Probably trivially, the higher accuracy here is better. So if training accuracy keeps going up, that means the model is getting better at the task on the training data, specifically the training data. Validation loss is the loss on the validation data. Validation data is held out from the training process. The model does not use it to update weights. So this gives us really a more honest signal of how well the model is doing on data that it is not directly training on. And then valid accuracy is the accuracy on the validation set. This is one of the most useful numbers to watch during training because it helps us see whether the model is generalizing well on data that it hasn't seen, instead of just getting better and better and better and better on the training data. If training accuracy improves and validation accuracy improves too, then that's usually a good sign that our model's learning well. If training accuracy rises a lot, but validation accuracy stops improving or even starts getting worse, that can be a sign of our model being overfit. However, on a simple MNIST model like this though, you'll probably usually see both improve pretty nicely. Let's visualize this. We have a few lines of code here that will help us visualize the accuracy over time. Run this, and we can see that training accuracy is going all the way up, and our validation accuracy kind of stays right where it is. We can see that our training accuracy improves greatly as we go on from epoch to epoch. The validation accuracy line will usually go up too, but it's a bit noisier. If both lines are improving, and they stay reasonably close to each other, then that's a good sign. It suggests that the model is learning useful patterns and not just memorizing training data. If the training data is much higher than the validation line, which we don't really see here, it means that we're overfitting. Let's do the same for loss. This is very similar, but now we're looking at loss instead of accuracy. If the model is learning well, we look for training loss going down and validation loss also going down. If training loss keeps dropping, but validation loss starts going up, that can be a sign that the model is starting to overfit. We can see here that the model is slowly starting to overfit, so we probably don't want to train all that much more. That would mean it's getting better at learning the training data specifically, but worse at generalizing. Using these curves, we can use them to diagnose how learning went and decide how many epochs our model should be training for. Let's evaluate the model on the test set. And we can do that using a model.evaluate here. Model.evaluate will run the model on data it did not see during training, and then it computes the loss and metrics. This is really important because the goal here is not just for the model to do well on the training data, and we wanted to generalize well to new unseen examples that we didn't use in our training process. That's what the test set helps us measure. We store the results into different variables, test loss and test accuracy. That matches the fact that we asked Keras to compute loss and accuracy. Then we print both values so we can inspect the final performance. This one here is super interesting. Test loss here is the mathematical error on the test set. The lower is better. It's useful alongside test accuracy because two models can have similar accuracy but different confidence behavior, and the loss can reflect that. We have test accuracy here of 0.974. And then that means that the model got around 97 to 98% of the test images correct. That's a really strong result for a simple neural network. Jumping down here, let's have the model make predictions on the test set. Model.predict here will return the model's output for each test image. Since the output layer has 10 neurons with a softmax activation, each prediction is a vector of 10 probabilities. So for one image, the output might look something like 0.001, 0.002, 0.950, 0.010, 0.003, and so on. Again, each position will correspond to one digit class, being 0, 1, 2, 3, and 4. Then we'll use np.argmax, which basically is saying, find the index of the largest value. Since the largest probability corresponds to the model's predicted class, argmax gives us the predicted digit. Now, after this line here, predicted labels is now a list of predicted digits. Let's look at some predictions. We can see that for this image here, the model predicted that this is a 7. And obviously, we can see here from a human looking at this image here, we do see a 7, a 2, a 1, a 0, a 4, 1, 4, 9, 5, and 9. If we sometimes see a mistake, sometimes a handwritten digit may be messy or even ambiguous, even to the human eye, so it makes sense that the model can get some of these wrong. Here, I think it would make sense here if the model predicted this as a 6, even though the true label here is a 5, because this is kind of difficult to interpret, and as a human, I could see this going as a 5 or a 6. It all just depends on your training dataset. Let's zoom in on an example. Let's run this. We'll take a look at our first block right here. Predicted probabilities here is a distribution, is a full probability distribution over all 10 classes. And this right here is the raw softmax output. Predicted labels with index will show the chosen class after we take the largest probability. So in here, we see that 7 is the class that was the most likely for this image to be. And then right here, we have our true label, which we know is 7. If one probability is much, much larger than the others, which you can see here, that means the model is relatively confident. If we see several probabilities that are somewhat close, that means the model is less certain and can see multiple classes as being plausible. Using these numbers here, we can start to see not just what the model predicted, but how confident it was in its prediction. At this point, let's ask ourselves, what did the model actually learn? The answer here is that it learned values for its weights and biases that help transform the 784 input numbers into output probabilities for the 10 classes. It doesn't learn digits the way a person does. Rather, it learned numerical patterns in the training data that tend to correlate with each class. Here, our model learned internal numerical relationships from many examples that we provided. And that's the heart of statistical learning right there. Even though the model here is really cool and a good first step, it does have its limitations. It's a toy example. Because we flattened the image into one long vector, the network is not really good at preserving the spatial layout of the image in a natural way. It can still work well on a simple dataset like MNIST, but it is not the most specialized type of model for image data, which is okay for now. And that's your first neural network in Python. We covered what a neural network is, how it learns from data, how images get represented numerically, how to preprocess the inputs, how to build the model, how to compile and train it, and then finally how to interpret the training results, how to evaluate it on test data, and how to inspect its predictions. If you enjoyed this video, make sure to like, subscribe, and check out my book, Modern Data from Ingestion to Production. Links below again. Thanks for watching, and I'll see you guys in the next one.